Alright folks, so we are back with another deep dive video, and in this one what we will do is we will do a deep dive into the multimodal models. So mainly we will concentrate on the vision language models, which we also call in short as VLM. So we will go through few of the architectures, the popular architectures that are currently in the market, and we will do a deep dive on how those architectures works, what are the building blocks, and how we can train those architectures with pre-training and the fine-tuning phases of those architecture. And then we will also see how some of the model works in terms of code. So we will also see models like clip and llama 3.2, how you can use it for image processing task or a image question answering task, right? So without further delay, let's get started. So first of all, what we generally have gone through in this channel, we have gone through a lot of unimodal models, which are like typically those are like LLM. So LLM generally accepts text as a prompt or input, then it generates the response. Right now, how the multimodal model is different is that it can accept different modalities as prompt or input. So here in this example, you can see one of the prompt is a text and the other one is a image, right? So it can accept a pair of input, which is text and image, and then it can generate the response. So that what we call as multimodal models. So typically people also send like video as one of the prompt or input to these models, and then they can ask certain questions about that video. But in this video, what we will do is we will talk about the vision language models, which can accept text and image as input, and generally that will output text as a response, right? So let's first go through few of the popular architectures that are currently in the market. So we will talk about two of these architectures. So the question is how we can pass the image as well as the text to a language model or the multimodal models, and how we can make them compatible, right? So what we generally use is we use a image encoder and a text encoder. So the image encoder will convert the image to image embeddings, and also the text encoder will convert the text to the text embeddings, which can be compatible, and then we generally send that to a pre-trained LLM, and then we get the corresponding response, right? So in that LLM, typically that LLM is a decoder based architecture where we have like few of the layer norms drop out, and the main component is the masked multi-head attention, along with the later layers which are like feed forward layers or the linear layer, right? So this we call it as joint embedding based decoder architecture. We have another architecture which is getting very popular with recent models like llama 3.2. So in that architecture, what we do is we pass the text to a text encoder, and the text encoder generally creates a text embedding, and then that we pass it through the pre-trained LLM, and at a later point of time when the marks multi-head attention layer, we send the image encoder output, which is again the image embedding of that, and that we feed it as a cross attention mechanism, right? So we will talk about in detail what this cross attention is and how that works in case of this architecture, what we generally call it as cross attention based decoder architecture. So we leverage the cross attention mechanism, which got very popular with the attention is all you need paper. Talk in detail how we can embed an image into an image embedding space, which would be compatible with the corresponding text that we will send as a prompt. So what we generally use is CLIP. So CLIP stands for Contrastive Language Image Pre-training. So that was released by OpenAI in the year of 2021. So this CLIP is a joint image and text embedding model that was trained using 400 million image and text pairs. So what the OpenAI did that time was they scrapped a lot of image and also the corresponding caption from the internet, and they kind of clubbed those as pairs, and then they trained the clip using a self-supervised way, right? So that will enable us to map both the text and images in the same embedding space, right? So that's why we call it as this joint embedding space. So this clip has mainly two components. So one of them is like a text encoder which embeds the text, and also it has an image encoder which will embed the images, right? So this text encoder is nothing but any of the popular transformer based encoder which they generally use in case of clip, and in case of the image encoder which is they use is the vision transformer, right? So if you are not aware of what vision transformer is, so I have created a video like how we can build a vision transformer from scratch using pytorch. So I will also provide the link of that video. Both this text and image encoder, they have trained from scratch using contrastive learning, right? So we will see how this contrastive learning works. But before that, if you are not familiar with VIT, so just a refresher. So this VIT will enable us to apply attention mechanism to the images. So to apply the attention mechanism to the images, what we generally do in case of the VIT is we create patches on top of the images. So you can see this image got extracted, and we extracted a lot of patches out of those image, and then we kind of create a linear projection of those patches to create a flattened patches. Then information we add the positional embedding to the patches, and then we pass it through the transformer encoder, right? So which generally uses the attention mechanism to create the embeddings which would be like much more meaningful, and which will be talking between each, right? Now let's get back to clip and let's talk about what this contrastive learning looks like, right? So the goal of this contrastive representation learning is to learn embedding space in which the similar pairs stay together, right? So the similar pairs are nothing but the text and image pair, right? So if you have image of a dog, then the text like this is an image of a dog, and the corresponding image will reside very closely in this joint embedding space, and the text and image which are not related, they will be very far away from each other, right? So what they generally do is they pass the text to the text encoder, and for each of the text they get the corresponding T1, T2, T3 as the text embedding, and the image also gets passed through a VIT which will create the corresponding image embeddings which are like I1, I2, I3 and the till the IN, right? Now this I1 and T1 is very closely related to each other. Give once you do a dot product between them, so that will give you a higher similarity. So the goal of this contrastive learning is to increase the similarity between the diagonal elements. So all these diagonal elements which will have a higher similarity, and the rest of the elements which are like row wise this element and the column wise this elements will have a lowest similarity, right? You can see we have the image which is I, and that gets passed through the image encoder which will produce the corresponding features related to the image, and then we will also leverage the text encoder and we pass the text through that to get the corresponding text embedding, and then what we do is we create a joint multimodal embedding. So what we do is we bring in learnable parameters which are like wi, which is related to image, and the corresponding wt. So using this learnable parameters, we kind of make this image embedding and the corresponding text embedding compatible to each other. And once that is done, then we normalize those values and we get the corresponding image embedding and also the text embedding. So once we do that, what we do is we do a scaled pairwise cosine similarity. So what we do is we calculate the similarities at the row level and also at the column level, right? So once that is done, then we calculate the loss. So you can see the loss are calculated at the row and also at the column level. Then we add those losses and divide by 2 to get a symmetric loss function using the steps, right? So I hope you got an understanding of how this clip mechanism works, where we generally try to increase the similarity between the corresponding pairs of image and text, and we will reduce the other pairs. So in that way we can create a joint embedding space where the image and text will reside in a same embedding space, and the corresponding pairs of image and text will have a higher similarity, and rest of the uh, pairs of image and text will have a lower similarity. So now let's see clip in action. So we will go through a code example. So you can see like we can do a certain type of prompt engineering where we have certain labels like plane, car, dog and bird. Then we create a text using each of these labels. So the labels will be like a photo of plane, a photo of car, a photo of dog. We pass it through a text encoder and we get the corresponding T1, T2, T3 and Tn, right? So once a particular image comes, which goes through the image encoder, and we get the corresponding uh, image embedding, which is like I1. So then we can calculate the dot products between each of these elements, and we will get a higher value which is related to the text, which is related to dog, right? So because this would be created in such a way that the similar type of text and embedding would be very close to each other, so that the dot product of I1 and T3 will give you a higher value, and based on that you can say that this is an image of a dog, right? So you can see we can download this model from a Hugging Face, which is OpenAI Click VIT base patch 32. So we will create a model, and then again we will create a preprocessor, and we will download the model. Once that is done, then we will get a dummy image, which is an image of a few of the cats, and then we can create this inputs. So at first we need to pass the text as well as the image through the preprocessor. So that will kind of ensure that the dimensions of the text and image gets certain changes, and then we once we get the inputs ready, that we will pass through the model, we will get the outputs, right? And then what we can do is we can get the similarity score between all the pairs, and if we take the softmax on top of those logits, we will get the corresponding probability, and we can see the probability is highest with the first text, right? So this text is related to this text, and this probability is related to this text, right? So we can see that the it has been correctly predicted that this image is of a cat. Okay, now that we have got a detailed understanding of how the image encoder works, now let's go through how the joint embedding based decoder architect training process looks like, right? So here we can see like we have the image. So image goes through the image encoder, and the text goes through the text embedding layer, and it produces the corresponding image embedding and the text embedding. Now to match the shape of the image embedding with the text embedding, what we generally do is we add a linear projection, so which will kind of match the image embedding shape along with the text embedding space, so that once we get the both of these embeddings, then we will do a concatenation, and then we will pass it through the LLM to generate the response, right? Now to talk about the training process, so typically for LLM also we have these two training steps, which are like pre-training and the instruction fine-tuning. So in case of this joint embedding based decoder architecture, we will have the multimodal instruction fine-tuning phase also. So the image encoder which we generally use is the pre-trained clip. So that will remain frozen during the whole training process, and we only train the linear projection, right? Which is a set of multi-layer perceptron, which are like 2-3 layers of multi-layer perceptron, and that we generally only train during the pre-training phase, right? So once that is done, then we will have also the LLM and embedding layer, so that are initialized with pre-trained instruction fine-tuned LLM, and this during the pre-training phase, this embedding model and the LLM remains frozen, and during the multimodal instruction fine-tuning phase, uh, this gets unfrozen, and we use the fine tuning of the weights of the LLM and the embedding layer to fine tune the model according to the instruction fine tuning process, right? So this typical example of this architecture are like Pixel and QWEN2VL. So these two models are based on this joint embedding based decoder architecture. Now let's talk about the other architecture, which is like the cross attention based architecture. I have gone through a lot of videos in this channel. So generally we have the decoder based LLM, which we have also recently implemented from scratch. So there the general architecture looks like this, where we have a starting dropout layer, then the layer norm, then we have the masked multi-head attention, and then the corresponding layers of like layer norm, feed forward, dropout, then the layer norm, and again the final linear output layer, right? So in case of cross attention, there in the decoder side, what we do is that we have a multi-head attention layer. So there the query generally comes from the decoder side, and the key and the value matrices generally gets passed from the encoder side. So typically the decoder based multi-head attention, which we have talked about so far, has this architecture where we have a single input, which is x1, then we multiply that x1 with the learnable parameters like wq, wk, and wv, and we get the corresponding qkv matrices. Then we do the matrix multiplication of qk transpose to get the attention matrix, and then we apply the scale dot product and the softmax to get the corresponding a matrix, which we again multiply with the v to get the final output. So this is what we generally use in case of the decoder based multi-head attention, right? So in case of our example, which is in case of multimodal, what we do is in the input side we concatenate the image embedding and also the text embedding, and then we send together this input to this decoder based multi-head attention calculation, right? Now how it differs from the cross attention is we will have two set of inputs, which is like x1 and x2. So the x1 is typically the output from the text embedding space or the text encoder space, and then we multiply that with the learnable parameter of wq to get the corresponding q matrix, and then we have the image encoder output where we get the corresponding k and v matrices using the learnable parameters like wk and wv, and then we do the dot product, and after that we multiply the v matrix to get the final output, right? So the only the difference is that we have two inputs in case of cross attention, the x1 and x2. So the x2 is flown from the image encoder side, and the x1 gets flown from the text encoder side, right? And then we finally do the attention mechanism to get the final output, right? So now let's talk about the training phase of this cross attention multimodal models. So we have this architecture where we put lesser inputs because we are only passing the text embedding through the LLM as an input, and then at a later point of time we pass the image embedding to the masked multi-head attention layer to do the cross attention, and we generally then do the other steps of this pre-trained LLM to get the final response, right? So here also we have two phases, the pre-training phase and the multimodal instruction fine-tuning phase. And the image encoder generally is a pre-trained clip. So during training, generally that remains frozen. So whatever the image encoder that we use, so for the typical cases, or there are certain exceptions which we will talk about very shortly, but generally this pre-trained clip is frozen. And the other things which are like cross attention layer, which typically remains unfrozen during the whole training phase. So whatever the calculations that are going using this cross attention in the masked multi-head attention layer, so those parameters remains unfrozen throughout the training process, right? So the exception which I was talking about, so that exception has happened in the recent model of Llama 3.2, where they have updated or trained the image encoder and the projection layer. So here also we use the projection layer to match the image embedding space, the shape of the image embedding with the text encoder. So that gets updated during the training phase. So in case of Llama 3.2, they have used a vision transformer with 630 million parameters, so that they haven't used the clip. So they have used a vanilla vision transformer, and then they have trained that vision transformer from scratch using this mechanism, right? And the language models, which in case of Llama 3.2, they have used the previous text models from Llama 3.1, and that remained frozen during the full training phase. So the explanation that they have given in the paper is that they have done to keep intact the language modeling capabilities of the 11B and the 90B models. So typically Llama 3.2 released a 4 set of models. 11B and the 90B models are text image model. So that they have kept frozen so that they can be used as a text model itself. So whenever the input has only text, so the text related outputs will be optimal. So that's why they have kept this language models frozen to keep intact the language model capabilities of these models, and they have only fine-tuned or trained the vision transformer, which they have used as a image encoder, right? So we can see this is the architecture of Llama 3.2, where image comes, the image goes through a linear layer, then the self-attention mechanism is there, feed forward is there, and that they have used, as I mentioned, like a vision transformer with 630 million parameters. So they have only trained this image encoder, and then they get image representation, which they pass as a cross-attention layer in the language model, and the text embedding space or the LLM they kept frozen till the full training phase, right? So the model they have used as a text model is like Llama 3.1, 8 billion, and the 70 billion model as a base model, and that they have kept frozen to keep intact the language modeling capabilities of this mechanism, right? And then we finally get the response using this whole architecture, right? So with this, let's go and see how the Llama 3.2 works in case of a small example where we pass the image as well as the text as an input. So yeah, so this is what you can see. At first I am installing Together, so because I will leverage the API of Together, so I am initializing the Together API key, then I am getting image. You can see this whole image, and that we will pass as an input to the Llama 3.2 90 billion model. So then I'm initializing the prompt. So in the prompt itself, I am passing the image URL and also the text input. The text is like what sort of animal is in this picture and what is the usual diet. So all this type of questions I have put in the prompt, and based on that I am calling the Llama 3.2 90 billion model, and we are getting the corresponding response, which is a text response. You can leverage vision language models. So there are a lot of use cases which people are doing currently, like you can generate a story out of an image, you can create a caption of an image, then you can also pass restaurant bills, then ask what is the total bill, what are the different components that has been ordered in that restaurant bill. So this type of use cases are getting very popular, so I see a lot of use cases will be used in the future also using this vision language model, right? So with this I will end this video. I hope you got a good overview of how the vision language model works and what are the internal components of this architectures, and we also talked about the two different architectures of this vision language model. Thank you. See you in the next video.